Hello, welcome to our first free GCSE biology stream. Who have we got in the chat? I posted a little hello so I know who we've got here. Welcome all. It's lovely to have you guys here. Who have we got in then? Post a little hello in the chat so that I can see that we have who we have here. Welcome. Who have we got? All right then, guys. Why did my screen do that? Never mind. Hi, Yashi. How you doing? Who else we got in then, guys? I can see we got Blah Blah here as well, and Chiru. Sorry if I'm mispronouncing your name, and Michal as well. So I'm just gonna put a little poll in the chat for you, team. Hi, Lulu. Hi, Sienna as well. I've put a little poll in the chat for you there. Who's already on a MES course? Who here is already on a MES course? Hello, Ishal and Matilde and Sangrid and James as well. Looks like we've got about 75% of you already on a MES course, maybe a little bit less than that, maybe 70% of you. Amazing. Yashi, I know you're already on a MES course there, Yashi. I recognize your name. Amazing, guys. Welcome to everybody. Welcome if you are new. Pronounced Sanjid. Fantastic. Sure, I'll try and make sure I get that correct. Welcome, welcome everybody. Welcome if you are not a part of a MES course as well. Excited for A-level biology. That's amazing, Matilda. You need to make sure you join our MES courses for your A-level biology. Now, what we're going to be doing today is a very, very quick, short, free stream just about osmosis revision. We're going to be looking at osmosis. We're going to be looking at the required practical. Blah, blah. This is absolutely for Combined Science Foundation. This is for higher tier. This is for triple science. This is for every single exam board as well. So everybody is in exactly the right place that they need to be. Now, for any of you guys that don't already know me, I am Joe. I am a biology teacher. I have been teaching for years. I have been teaching at some of the top schools in the country, including kind of one of the top schools in London. I was the head of biology at that school as well. Welcome, Ben. Welcome, Sal. And also, I'm an examiner. I'm an examiner for AQA. I have marked exam papers. And the thing is, I know exactly what the examiner is looking for. And that's what I really want to get across to you guys. I want to give you those tricks, those little hacks, those tips so that you can nail your exams and you can make sure you get full marks. Sometimes your exams, it feels like jumping through invisible hoops. I want to make those hoops visible to you so you know exactly what it is you need to say. All right, enough waffle from me. Let's crack on and let's get started. Welcome, Israel, as well. Can I mark yours in the exam? Unfortunately, I'm not actually marking this year, okay? There, Chi, I'm not actually marking. This is definitely paper one there, Nadia, yes. Okay, so we're looking at revising osmosis to begin with. We're going to talk about how to investigate the factors that affect osmosis and how to determine the concentration inside a cell. So let's get started by thinking about osmosis. So into which cell is water going to move the fastest? We've got P, Q, and R. Post your answer into the chat, team. P, Q, or R. Which one do you think the water is going to move into the fastest? Yashi in there straight away with the R. James says P. Neve says R. Chirui says R. And Ben says R. It looks like we've got a little bit of a consensus on the R, which is absolutely correct. The next question is why? Hello, NK. Thanks for joining us. Welcome. Why is the water going to move into cell R the fastest? Matilde saying it has the highest concentration. The highest concentration of what, Matilde? The highest concentration of sugar, Yashi says. So it's got the highest sugar concentration. And if it's got the highest sugar concentration, what does this mean that we have the greatest? K saying the greatest concentration gradient. Exactly there, K. Fantastic answer. So we've got the greatest concentration gradient. But what are we missing here? We still haven't said there's something missing. What does this mean? The greatest concentration gradient means we're going to get the fastest rate of... So we're going to get the fastest rate of... What are we missing? What is our big key word that we need to add in here? Exactly there, Kay and Matilde. It is osmosis. Because ultimately we are talking about the movement of water. Fantastic. Yes, well done, everybody. Well done, James. So what do we mean by osmosis? I'm going to throw this out here. I'm going to challenge you to give me the perfect definition. There's a perfect definition that examiners love to see in your answers. What is your perfect definition? Not quite the same, Yashi. Not quite the same. No. You're joining those year 11 streams there, Yashi, from year 9 and 10. What's going on? What is that perfect definition? So Mathilde says the diffusion of water. So Mathilde talking about water potential. Ooh, showing off there, Mathilde. You're just slightly the wrong way round, though. It would be high water potential to low water potential. Hello there, Chaos. Welcome. Very nice there, Sajid. Movement of water from dilute to concentrated. I love that. So our osmosis. Some of you guys have missed this idea of net movement, because remember, it is going to be occurring in both areas. So it's the net movement of water from the dilute area to the concentrated area through or across that partially permeable or semi-permeable membrane. Excellent there, Knight. So across a semi-permeable membrane. What's an example of a semi-permeable membrane then? So this semi-permeable membrane, what's an example of that? What do we mean when we talk about a semi-permeable membrane? What's an example of that semi-permeable membrane? Yashi straight in there with an answer. Very, very good. What else are we saying, team? Any thoughts, Jake? Any thoughts, Ben? Sal as well. Oh, not just the intestinal wall. We're thinking the cell membrane, guys. We're thinking the cell membrane is that semi-permeable membrane. So the cell membrane is our example of a semi-permeable membrane. What it does is it's selective. It controls what can pass through it. Some things can pass through, some things can't pass through. So if I had a kind of beaker here with a semi-permeable membrane in between both sides and the same amount of water, but on one side I had lots of my solute particles and on the other side I only had a few of my solute particles, what direction is the water going to move in? Is it going to move to the left or to the right? Post your answer into the chat then, team. Left or right? What direction is the water going to move to? Kay says right to left. Ben says to the right. Sal says left to right as well. Sajid says to the left. Well, our definition says it's going to go from the dilute to the concentrated area. So this area here, is this concentrated or dilute? If we've got lots of solute particles, is this concentrated or dilute? What do we think? So that left-hand side, is that concentrated or dilute? Very nice, Yashi and Ben. And Sal, yeah, this is going to be our concentrated, which means that this is the dilute area. It's the area where there is not much of that solute, or there's less of the solute. And so the water is going to move from our dilute area to the concentrated area. It's going to move to the left. Fantastic there, Agona and Mathilde and Knight too. Great there, team. So the water is going to move in that direction. And we really want to think about that, because when we think about dilute and concentrated solutions, sometimes it can be a little bit sort of different to how we think about them normally, because we're not talking about the amount of solute. We're thinking about the amount of water in relative terms compared to the amount of the solute. So osmosis is our special case of diffusion. What are the factors that affect the rate of osmosis then? What are our factors affecting the rate of osmosis? Shout some out on the chat. Let's see if we can name all 4, and then we're going to go through and explain them in a bit more detail. Kay getting in there quickly with the temperature. Fantastic. Very good there. Kenzie as well saying temperature too. So we've got our temperature. Excellent. We've got Neve getting in there with the surface area. Fantastic. So we've got our surface area as well. We've got Mathilde saying the concentration gradient. Fantastic. So I'm just going to put our conc gradient there for concentration. And one more as well. One more. I haven't seen anybody saying it yet. Oh no, Sal's mentioned it. And Sajid has mentioned it as well. Our diffusion distance, or our kind of distance there. So thinking about our temperature, if we increase the temperature, how is that going to affect the rate of osmosis? If we've got a higher temperature, Why does that affect the rate of osmosis? What do we think? What do we think? If we've got a higher temperature, how is that affecting the rate of osmosis? Kay saying increasing osmosis, very good. Ben talking about increasing kinetic energy, excellent. What else could we say there, team? So increasing temperature, we've got increasing osmosis because we have increasing kinetic energy. Those particles are moving faster, aren't they? They're spreading out faster. NK, this is absolutely going to be an edXL as well. Absolutely going to be an edXL. All right, let's go to surface area. Now, surface area, if we increase the surface area, how does that affect the rate of osmosis? How does that affect our rate of osmosis? If we've got an increased surface area, how's that going to affect the rate? A larger surface area increases the rate of osmosis, more frequent increasing as well. Kay says, yeah, very nice. Kenzie too. So increasing osmosis. What might be an example of an adaptation to increase surface area? What could be an example of an adaptation that is going to increase that surface area? That's going to make sure we absorb the water faster? Kenzie saying the villi, Sal saying the microvilli. Very nice. So microvilli slash villi. Remember, the villi is the large structure made of many cells. The microvilli are the little folds on the villi. Chi saying the root hair cell. Love that as well. So we've got our root hair, because that is another adaptation. Remember those plant adaptations. It's only going to be about half an hour, Blast, so we're going to be finishing at about 8 p.m, okay? Concentration gradient. Let's go back to our concentration gradient then and now. If I increase our concentration gradient, let's just pause for a second. Yeah, great question, Chi. What is concentration gradient? What do I mean by this word concentration gradient? What do I mean by this? When we looked at that first example, we said that cell R had the largest concentration gradient. But what do I mean by that? Yashi says the difference in concentration. Kay says the difference as well. And Neve as well. Yeah, fantastic. The concentration gradient is very simply, it's just the difference in concentration. Scientists, we love giving things fancy words. So that's all it means, the difference in concentration. If you increase the difference in concentration, what's the effect of that going to be? So if I increase that concentration gradient, how is that going to affect the rate of osmosis? If we have a larger difference in concentration, again, great there. Kenzie, it's going to increase that concentration gradient. Fantastic. Night as well. It's going to increase the rate of osmosis. And then finally, we have our distance. If we have a decreased distance, hopefully this is a bit of an obvious one. If we decrease the distance, what does it mean for those particles that are moving? It means it's going to take less time. Very good, Sal. So that's going to increase the rate of osmosis. What would be an adaptation to decrease the distance? What would be an adaptation to decrease the distance? What do we think? Being one cell thick. Very good. A one cell thick exchange surface. Thank you very much, NK. I love that. So what we could say is that we could have a one cell thick exchange surface. One cell thick exchange surface as well. Amazing. Good. So yeah, capillaries being one cell thick. We could talk about the kind of alveoli being one cell thick. We could talk about the walls of the intestine being one cell thick as well. Lots of different examples of those exchange surfaces. So that's our kind of overview of osmosis. This would be suitable for higher, foundation, triple, combined. Absolutely everybody needs to know this in detail, Kenzie, okay? So osmosis, the practical. This is the hard part. This is the required practical. We need to know this in a lot of detail. So whenever we think about an experiment, we need to identify our 3 different variables. Let's just do a bit of a recap on our independent variable. What do we mean by the independent variable? What do we mean by the independent variable? Can we do a question about it? Yeah, we've got an exam question to do at the end, blah. The independent variable is what we change. Very good. What about our dependent variable then? What's the dependent variable? Really good, team. Very good, Sienna. If it changes, it's what we measure. Yes, lovely. It's what we measure. And then what about our control variable? Nice there, Phoebe. What about our control variable? Which one is that? It is what we keep the same. Keep the same as well. Good. So in this instance, what we are trying to do is we're trying to determine the concentration inside the potato cells. Why do we want to do that? Why do we care what the concentration inside a cell is? Well, imagine we were trying to do a blood transfusion. Imagine we were trying to put some solution, some saline solution into someone's blood vessels. Well, we want to make sure we don't damage those blood cells. And so we want to make sure it's the same concentration as the blood. And to do that, we would want to do an investigation like this. So what are we changing between these 5 different potato cylinders, or 6 different potato cylinders? What are we changing here? What is the independent variable? It is the concentration. Exactly, Sal. Exactly, Kenzie. Yeah, it is the concentration of the solution. And then I'm going to measure how that solution affects the cells. How am I going to measure that? What am I going to be measuring? What am I going to be measuring? What is the dependent variable here? What am I actually going to measure? I'm going to measure the mass, or the change in mass specifically, aren't I? It's the change in mass that I'm going to investigate. And then I'm going to need to keep a whole load of things the same. Kay mentions the percentage change in mass. Very good. I'm going to come to that in a second there, Kay. Very nice there. GTR saying the mass of the potato. So the control variables, what do I need to keep the same? What do I need to keep the same? What do I need to keep the same for those control variables? What else am I going to infect? What else am I going to investigate? The surface area of the potato. I want to control the surface area of the potato. Good. What else might we need to control? What else might affect that? Neve says the time in the solution. Lovely. Because if I leave them in for longer, more osmosis takes place, doesn't it? Not the mass, because potentially the starting mass, but we're going to come to that in just a second. Kenzie says the temperature. Excellent, Kenzie. The temperature. Very, very good. We'd also want to control the temperature. So let's talk about starting mass. Let's talk about starting mass, but also the surface area. Now, is it possible for me to make sure that the pieces of potato are exactly the same size, exactly the same surface area, exactly the same starting mass? Is it possible for me to be that precise with my little scalpel, maybe under a microscope, making sure they've got exactly the same, maybe making sure it's got exactly the same number of cells? No, it's not possible. It's not possible for me to make sure they're the same. So there might be differences in the starting mass. Now, if there's differences in the starting mass or the surface area, well, I want to account for that. I want to make sure that I can compare my different potato cylinders. So what I'm going to do is I'm going to use percentage change. Percentage change allows us to compare for different starting masses. So the percentage change allows for comparison. How else could we make sure these results are repeatable or improve the quality of our results? Am I just going to use one potato cylinder? What else could I do to improve the precision of my results? How could I make my results more precise? Very good there, Kay. Exactly the right phrasing. Repeat and calculate a mean. Very good. Repeat and calculate a mean. Excellent. And potentially we could say alongside that, we could say remove anomalies as well. We could remove any anomalous result. Remember, those anomalies are the outliers. They are the results that don't match the trend of our data. And then let's have a little think about what have we missed here. There's something else that's going to affect our results. When I remove that piece of potato cylinder, it's going to be covered in water, isn't it? It's going to be wet. This would be for absolutely everything, NK, foundation and higher, okay? I'm going to blot it with that paper towel. I'm going to remove the excess water. So I'm going to remove the excess water or the surface water with a paper towel. Because what that's going to do is that's going to affect the results. Remove the excess water with the paper towel. Great there, guys. Very, very good. Okay, so what do we need to do? This is a graph that you might have to draw in your exams. And in your exams, you need to give a suitable scale. Now, if I was to look and give a suitable scale here, let's imagine we've got 0. I'm going to go 0.1, 0.2, 0.3, 0.4. Is this good? Is my graph good? Have I done a good scale? I've made 2 mistakes. What are the 2 mistakes I've made for my scale of my graph? It's not good, is it, Kenzie? Absolutely correct. It's not good. B7 says it's not good. What are the mistakes I've made, guys? What are the mistakes I've made? If there was an anomaly on the graph and it asked to explain why, you could say they didn't dry it. Yeah, very good, Matilda. Very good. So that not drying it could lead to the anomaly. Doesn't cover half the page and it's not labeled as well. So let's correct my error. Let's make sure we've got an evenly spaced scale, 0.3, 0.4, and then I'm going to label it as my concentration of salt solution. And when you label your axes, make sure you give your unit as well. Always make sure you write the unit of your axes there. Writing into my head slightly. I'll move my head out of the way. All right. So now I'm going to plot my data. So I've plotted my data using X's. I'm going to use large crosses to plot my data. And that way my data is nice and precise. Okay. Make sure you use a pencil when you are plotting your data on your graph. And then I'm going to do my line of best fit. Looking at this data, do you think it's a curved line or a straight line? SR getting in there saying a curved line. Anybody think it's a straight line? Kenzie says curved. Yashi says curved. Neve says curved. Everybody's saying curved. It looks like a curve, doesn't it? It looks like a curve. So we're going to do a curved line of best fit. We're going to do a curved line of best fit exactly like that. And we're going to try and do a smooth line through all of those points. Very, very good. Hi, Pranav. How will the examiner mark the graph? Great question, Chi. So the examiner, what they're looking for is more than half of the grid is used. They're also looking for a sensible scale. No 3s, no 4s, no 7s, 6s, 8s, 9s, a sensible scale. We're also looking for the label for the axes with units. So the labeled axes. Labeled axes with units. We're also looking for a line of, or like accurately plotted points. Let's do them in order. Accurately plotted points. This is usually worth 2 marks. Plotting the points is usually worth 2 marks. And then we're going to also think about our line of best fit. I'm going to put LOB there, line of best fit. Any tips for drawing those line of best fits? Pencil, firstly. Make sure you use a pencil and try to do it in a smooth curve. If it's a straight line of best fit, use a clear plastic ruler that's 30 centimeters, so you've got lots of length. Trying to do it on a 15 centimeter ruler and trying to move the ruler up isn't going to help. So we want to use a clear 30 centimeter ruler, and then we can try and join those points together. And if you need to, rub it out and redraw it, okay? You can rub it out and redraw it, and that's why you need to use a pencil. So using your graph to estimate the concentration of the solute inside the potato cells, which point am I looking for here? How am I going to determine that? When it's the concentration of the solute is inside the potato cells, if I have a cell and we have 0 net movement, no, if you rub it out, Kenzie, if you rub it out and then it's clear where your new line is, then you would get the mark, okay? How many marks would you get taken off if you did a straight line instead of a curve? Just 1, Sienna. So the line of best fit would be worth 1 mark. We're looking for where it crosses the x-axis. Fantastic there, SR, fantastic there, Sal and Knight as well. We're looking for the x-intercept here. So we're looking for that x-intercept. And the reason why is because we have the zero change in mass. If we've got zero change in mass, that means we've got equal movement inside and outside of the cell. So zero change in mass. And if we've got zero change in mass, what is the how would we describe this solution? How would we describe this solution? What's the key word here? This is more of a sort of triple only topic, triple only term. What is the key word that we would have here for our cell? There's no change in mass. It's the same concentration inside and outside. Great there, team. Very nice there, Sal. It is isotonic. Excellent. Isotonic, as Knight says. So we can see here we're at about 0.31. So 0.31 mole per decimeter cubed. Perfect. It is isotonic. Exactly, Mathilde. Okay. Let's do a quick exam question just to go through this then, just to remember how we do our percentage change calculation as well. So explain why osmosis is important for plant cells. Why is osmosis important? I am stumbling over my words. Don't worry, Kenzie, if you didn't know the word isotonic, it's I don't think you'll ever get asked a question about it, actually. So absorb the mineral ions. It's not about absorbing the mineral ions there, SR, because remember the mineral ions are going to be absorbed by diffusion. So the water can move into the cells. And why does the water need to move into the cells? So water moves into the cells to maintain what? Why do the cells need the water? Maybe for photosynthesis, but there's a slightly bigger need. Who was it? Somebody already mentioned it. I saw the word. Mathilde mentioned it. About the shape, the turgor pressure. To maintain the shape of the cell. And that word turgor pressure, to keep the cell kind of inflated, the turgidity. Great word there, Yashi. And why is that necessary? Why is maintaining the shape of the cell important for a plant? How am I going to get my second mark here? A stable shape could be another way of saying that. Yeah, good blah. Why is the shape of the cell important? So it doesn't fall over. Yeah, to maintain the support of the plant. So to maintain the support of the plant. To maintain the support of the plant. Great. And then calculate the percentage change in mass for the potato cylinder placed in the 0.8 mole per decimeter cubed sucrose solution. So the 0.8 mole per decimeter cubed, our percentage change is equal to, what's our equation for percentage change, team? How am I going to work it out? Blah blah's already gone ahead and worked out the answer. Fantastic. What's our equation for percentage change? You guys are going ahead and working out. It is our change, it is our difference minus our original value multiplied by 100. So our change there is going to be our 1.55 minus 1.35 divided by our original value, which is 1.55 times 100, and we get a change of minus 12.9%. Why is it negative? Why have we got a negative value? Why have we got a negative value? Let's just finish on this then. Why have we got a negative value? It decreases in mass. It decreases in mass. Why does it decrease in mass? Decreases in mass because water has moved out of the cell. Water moves out of the cell. And I'm going to leave you with this final exam tip. In your GCSE exams, whenever you talk about the movement of water, always say by osmosis. Okay? Always say by osmosis. Always say it, because often you get an additional mark just for saying by osmosis. Sometimes you have to say by osmosis in order to get the mark. So just always say it. Always say water moves by osmosis. Simple as that. All right, amazing team. Thank you so much for joining. Tell all your friends, because next Monday we are going to have another free stream. I want as many people there as possible. I want to smash it. I want to help everybody in the country get good grades in their GCSEs. So tell as many people as you can. Tell them to join. I'm going to put it on my TikTok. I'm going to put it on my Instagram with the link to get signed up as well, because it will be a different link to the one today, because it will be a different live stream. And yep, every single Monday, Sal, every single Monday. All right. Who signed up for the cram course as well? If you haven't signed up for the cram course yet, get signed up for the cram course. Give this video a like. Share it. Come on, get everybody involved. Get everybody involved. Let's tell everybody in the country to get involved and get this free biology lesson, this free biology tuition. Yep, same time, 7:30. It will be similar to these lessons. It's not going to be exactly the same. It's not going to be exactly the same. What are we doing next week? We're going to be looking at the enzymes experiment next week. Okay. Am I doing my lesson tomorrow at 4:30? Yeah, I am doing the main course lesson tomorrow at 4:30 as well, Sienna. Yeah. Yeah, I am doing the main course at 4:30. Okay. Fantastic team. I will see everybody next week, and I will see more people next week. Tell everybody. Thank you so much, and I will see you next time.